Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. In this video, we are going to continue our discussion on the queuing system and we are going to explore a new type of queuing system. So far we have done MM1 system, which was section 20.4. Today, we are going to look at MM1 GD C infinity, and that's section 20.5 of the textbook. So first tell me, and in the MM1 which we did, this is GD infinity infinity, and we said if we have GD infinity infinity, we may not, I mean we are okay if we drop it. However, here we are looking at MM1 GDC infinity. Can you tell me what is the difference between in this system and the previous system that we learned?
The amount of people that are allowed in the system is not infinity?
The size of the population is this one. So I would consider this as the size of the system. Yeah. So yeah, the number of people that are allowed, or the size of the population. So the size of the population is limited, is C, and is not infinity. In the previous scenario, the size of the system is limited. In previous system, the size of the system is not limited, as even if we have infinite number of customers, they can come to the system and we have no problem. But here the size of the system is limited. Because of that, so what are the possible values for number of people in the system?
Any real number, integer,
All the way
besides infinity?
all the way to infinity?
Well, infinity isn't a real number, so I'm guessing like any real integer? Or is there a set limit in our book?
It would be to C, 0, 1, 2 to C.
All the way to C, because C is the size of the system. C is the size of the system, so we cannot have more than C entities in the system. So the size of the people in the system can go all the way to C. And then we also assume, again, that the rate of arrival to the system has nothing to do with how many people are in the system. No matter how many people are in the system, the rate of arrival is lambda, and no matter how many people are in the system, the rate of the departure is v. Okay. Then we can show that for pi j, which is number of people, with the probability that there are j people in the system, is pi 0 cj, which is the same formula that we extracted for the general queuing system. And then cj, if you remember, we extracted, which was rho to the power of j, and as a result, this is going to be pi j equals to pi 0 rho to the power of j. And then if I wanna calculate, and in this formula, obviously I know rho is lambda over mu. We always know lambda, we always know mu, so we know rho. So in this formula, similar to what we had for the previous system, if I can find the value of pi 0, I can use this formula and find the value of pi j for all j's. So to be able to find the value of pi 0, then I can write the famous summation that pi 0 plus pi 1 plus pi 2 all the way to pi c. This sum equals to
1.
And so this is pi 0 plus rho pi 0 plus rho 2 pi 0 all the way to rho to the power of c pi 0 equals to 1. And then if we write the formulation, so this is basically going to be pi 0 equals to 1 over 1 plus rho to the power of j from 1 to c. And if we do the calculation, given the fact that we know rho is between 1 and 0, then this summation is going to be, we can show similar to what we did in previous session when I calculated the infinite sum for you. We can calculate this sum and we can show that pi 0 equals to 1 minus rho divided by 1 minus rho to the power c plus 1. Okay. So again, as you are taking the note, make sure to write down the title of this queuing system on the top of, as the heading of your note for this section. And as you write down the formulas, make sure to put them in a rectangle or something so that you know these are the important formulas that you should know, so that you know exactly which one you have to pick depending on the type of system that you may have. Okay. So that's going to be the pi 0, and then given the, if I have pi 0, and I also have the value of rho, then I can calculate the value of pi j. I can calculate the value of pi j, which is the probability of having j number of people in this system. Then we also calculate L. And can you tell me how do we calculate L? Given the fact that we know possible values for number of people in the system, and we know the probability associated with each one of them, pi 0, the probability that there are 0 people in the system, 1 person, 2 people, all the way to c people in the system. Can you tell me how I can calculate L, which is average of number of people in the system?
Rho over 1 minus rho.
No, just tell me the formula. So if you know number of people in the system, which are 0 or 1 or 2 or 3 all the way to c, and you know the probability of each one of them, how do you calculate the average of this random variable? Here. Don't you need to multiply each random variable by its probability? So L is average number of people in the system, right? Possible values for number of people in the system is 0, 1, 2, 3, all the way to c. And I know the probability that each one of them can happen. So if I want to calculate the average number of people in the system, so for that I only need to multiply by possible number of people in the system by its corresponding probability and add them together. And here j goes from 0 all the way to c. So that gives me the average number of people in the system. Pi j, we already know the formula for pi j. So if I put the formula for pi j and do the simplifications and so forth, this is what L is going to be. It's a little long, so I'm going to write it here. Okay, so this is the formula for L. I'm not going through the extractions and everything, but this is basically the logic behind the formula. And then after we put the value for pi j and j's and do the simplification, this is the final value for L, which is average number of people in the system. And then, can you tell me what is LS? What does it measure?
Average.
Average number of people in
The queue. Service.
and
Service.
and the service area. In the queue is LQ and the service area. So now tell me, and this is an MM1 system, right? This is an MM1 system. I have only one server. Tell me what are the possible values for number of people in the server. I want to calculate average of number of people in the server, right? I have to find out what the possible values for number of people in the server and then multiply each one of them by the corresponding probability and then add them up, and then I have LS. Tell me what are possible values for number of people in the server.
1.
Or
0.
0. When there is no one in the system, there is no one in the server. And when okay, so let's think, let me answer this. Okay, so possible values are 0 or 1. So this is MM1 system. There is one server, so there is always either no one in the server or there is one person in the server. Tell me when we have 0 people in the server. When would that happen? When we have 0 people in the server.
That the customer has been serviced and exited the system and the next customer is yet to arrive.
No, we never want to, so that's just something we don't want to count. So when the customer has left the system and the next customer is yet to arrive, what is that scenario?
The server's idle.
When there's no one in the system, right?
Yep.
So that's the scenario when there is no one in the system. And when would that happen? What is the probability that we have no one in the system?
Pi naught.
Why not? And then, okay, so now tell me what is the scenarios under which we can have one person in the system? What is the probability that we have one person in the server?
Pi 1.
Is that the only scenario? Pi 1
Plus
is,
pi naught.
can you repeat one more time?
Plus pi naught. Because it's, did you say at least 1?
No, I didn't say at least. This
Oh.
one means there is one person in the server. Then what are the scenarios under which one person is in the server?
Pi 1.
Pi 1, it means there is one person in the system. So since we have only one server, if there is one person in the system, the person immediately goes to the server and gets the service and leaves. And is that the only scenario?
No.
What are the other scenarios?
The other scenarios would be whenever there's people in the queue.
Okay, so basically when there are 2 people in the system, or 3 people in the system, or 4 people in the system, or anything. So as long as there is more than one person in the system, the rest are going to stay in the queue and this server will be always busy. So as long as there is one person or more than one person are in the system, the server is busy, right? And that's the probability that those scenarios that can happen. And there is one person in the system, or 2 people, or 3 people, or 4 people, and so forth. Now, so the LS, which is average number of people in the server, we know that there is one server here. There are 2 possible values for number of people in the server, either 0 or 1. 0 happens with probability of pi 0, 1 happens with this probability. Now, tell me, how do you calculate LS, which is average number of people in the server?
Don't we do it the same way we did it with L, just multiplying all the probabilities together?
Okay. So this part is 0. Then LS equals to pi 1 plus pi 2 plus pi 3 all the way to infinity, or 1 minus pi 0. So this is the formula for LS. Given the fact that I know L and I know LS, can you tell me how can I calculate LQ?
L minus LS.
Exactly. L equals to LS plus LQ. So if I have L, then I can say remove number of people that are in the server, then that gives me the number of people that are in the queue. So given the fact that we know how to calculate L, we know how to calculate LS, then I know how to calculate LQ. And then the other things that are left, so we calculated L, LS, LQ. We calculated the formula for pi j's and pi 0. What are the other things that are left?
W.
W, WQ, and WS. So we know the formula for W, right? The Little's formula is L equals to lambda W. And then here, the lambda is the rate of, is basically the rate of arrival to the system. But when I say arrival, I also mean entrance to the system. So in everything, everything we have done so far, for example, for MM1, the size of the system was infinity, right? Everyone who arrived entered the system as well. So this lambda that is used in the L equals to lambda W in the Little's formula, this is basically the rate of entrance to system. We didn't worry about that in previous system because the size of the system was infinity. Because the size of the system was infinity, and we didn't have any limit on how many people can enter the system. So anyone who arrived entered as well. So basically, the rate of arrival and the rate of the entrance were the same. So I was okay. However, here, since the system has limited capacity, since the system has capacity of C, not everyone who arrives to the system can enter, right? So since the system has limited capacity of C, not everyone who enters, not everyone who arrives can enter. As a result, I have to calculate the rate of entrance to the system. And this rate of entrance is exactly what I need to put here for lambda. So what is the rate of entrance? So if there are C people in the system, so the system has capacity of C, right? The system has capacity of C. If there are C people in the system already, what is the rate of arrival? Zero.
They're just lambda, so the same, so 0.
But if there are C people in the system is full, right?
Yeah, so C.
So 0. No one would come to the system. When pi C percentage of the time, when there are C people in the system is full. So no one can, the rate of arrival is lambda, but the rate of the entrance is 0. Okay? And if the system is not full, which is 1 minus pi C, anything other than pi C, if the system is not full, then the rate of entrance to the system is lambda. Anyone who arrives potentially can enter the system. Okay, so if there are C people in the system, 0 people can enter. The rate of entrance is 0 if there are C people in the system already. If there are not C people in the system with probability of 1 minus pi C, then the rate of entrance to the system is equal to the rate of the arrival. So anyone who basically enters the system, anyone who arrives can enter the system. Okay. So this means that basically the rate of entrance to this system is lambda 1 minus pi C. And just keep that in mind when I want to use this Little's formula to calculate W. Just keep that in mind that instead of just simply putting lambda, I need to put the rate of entrance to the system, which is this. So then L is going to be lambda 1 minus pi C W. Then this is how the formula would change in this system. If you have L, which we already know how to calculate, if we know lambda, which we know for any queuing system, we have to know the rate of arrival. If I can calculate 1 minus pi C, which we can because we learn how to calculate pi j's, then we should be able to find W using this formula. And then you can use this formula also to calculate WQ. Okay. And what is WS? I mean, we can calculate WS to just say, oh, W minus WQ is WS, but can you also tell me in a different way, what is WS? The time in the server. If you know the service rate is mu, what is the time in the server?
1 over mu.
1 over mu. Okay. So we can use that as, for example, if I calculate L using this formula, if I calculate WS using this formula, then I can just say, oh, WQ equals to W minus WS and find WQ, or just calculate it using this formula. Both of them are fine.
Okay, so as you take note, we are still in the second queuing system, section 20.5. In the first example, we have a server, example 1. So in this example, we have a server that can provide service to 2 customers per hour. And then on average, three customers per hour also arrive to this system. And one other thing that we know is that inter-arrival and service times have exponential distribution. And also the capacity of the system is 3. System has limited capacity. That's the whole point of C here. And system can hold only 3 entries or 3 customers in the system. Okay, so so the service time is on average 2 customers per hour. Arrival rate, so that's service rate. Arrival rate is 3 customers per hour, and the inter-arrival time and service times are exponentially distributed. That's why we are sure that this whole MM thing holds here, because inter-arrival time and the service times have exponential distribution, so that takes care of the MM part of this queuing system. And the capacity of the system is 3, and system has 1 server. It hasn't mentioned, but by default system has 1 server. Okay, so now we want to see the first part. What is the probability that server will be busy? So I may ask, what is the probability that the server is busy, or what percentage of time the server is busy? I can ask that question as well, percentage of time. So I may ask, what is the probability that the server is busy, or percentage of time? What is the percentage of the time that the server is busy? What do I need to calculate here?
1 minus pi naught.
1 minus pi 0. Okay, because pi 0 is the chance that the server is busy. If we don't have pi 0, then we have pi 1. What are the other options other than pi 0, René?
If I remember correctly, since our system has a capacity of 3, we can do 1 minus pi.
When you say 1 minus pi 0, what else is left here? So what are the options? So this means the chance that the server is busy. So can you tell me in the other way? So the server is busy when there is 1 customer in the system, or?
2 customers in the system or 3 customers in the system.
Can I go to pi 4?
You cannot because capacity is only 3.
Exactly. So I cannot go to pi 4 or 5 because capacity of the system is 3. So pi 3 is the highest I can go, the chance that there are 3 people in the system. So the chance that the server is busy is 1 minus pi 0. Or I can calculate pi 1 plus pi 2 plus pi 3 because if there's 1 person or 2 people or 3 people in the system, for sure the server is busy because there's just 1 server in the system. These people are not going to stay in the line if server is idle. So they definitely go to the server, so the server will be busy. And we also showed that in previous session that the pi 0 is 1 minus rho over 1 minus rho to the power of c plus 1. And then rho is lambda over mu. What is the arrival rate here, guys?
That's the serviced. That's 2 customers per hour.
3 customers arrive. Yeah, here. No, 3 customers per hour arrive. That's arrival rate, right?
So that's
3
your,
cus- 3
that's your
cus-
lambda. Sorry.
no worries. And then the service rate. The server provides service to 2 customers per hour, so 3 over 2. Okay. So the arrival rate is 3 over 2. And as you can see here, remember we always said in every queuing system we look at so far, we said the arrival rate, I want this to be less than 1, between 0 and 1. That was the condition that we wanted for any queuing system, for it to be stable and the number of customers in the system doesn't explode. Why here we are okay with rho greater than 1?
Because there's a capacity?
Because there is a capacity in the system. So the system has capacity of 3, and the number of customers in the system will never go to infinity, even the rate of arrival, even if the rate of arrival is greater than the rate of departure, which is the case here. The rate of arrival is 3, the rate of the departure is 2. The more customers come to the system than the ones that leave the system, but still the number of customers will never go to infinity because there is a limit on the capacity of the system and how many customers can be in the system. So we don't need to worry about rho less than 1 in this scenario. Even if rho is greater than 1, that's fine. So rho is 3 over 2 here. Then pi 0 is going to be 1 minus 3 over 2. 1 minus 3 over 2 to the power of 3 plus 1. That's going to be 16 over 130. And then 1 minus pi 0 that we wanted to calculate to be able to find out the percentage of the time that the server is busy is 1 over 16 over 130. That's going to be 114 over 130. Okay. Which means a high percentage of the time, actually, I don't know exactly the number, right, by something around 90% of the time, the server actually will be busy with this rate of arrival, which makes sense. The rate of arrival is greater than the rate of departure. So a large percentage of the time the server will be busy, which, okay. So that's part A. Any question?
No.
Go ahead. You said no, John?
Correct.
Okay. In part B, I want to know on average how many potential customers can enter the system. Okay. One point that I mentioned in previous session when we especially wanted to calculate the L, remember when we wanted to calculate L, so this is just in parentheses. So when we wanted to calculate L, we always say L equals to lambda multiplied by W, right? However, I mentioned in previous session that lambda is the rate of arrival to the system, and always the system that we looked at so far had no limited capacity, right? So the rate of arrival to the system was equal to the rate of the entrance to the system. However, when the system has limited capacity, then the rate of arrival is not equal to the rate of entrance to the system. Not everyone who arrives to the system can necessarily enter the system. The lambda that is used in all these formula that we have set so far is the rate of entrance to the system. Okay, that's the lambda that we have used in all the formulas, is the rate of entrance to the system. And so if I want to put the rate of the entrance to the system in this formula, then I have to calculate that. So given the fact that if I have the arrival rate, then from that I have to calculate the rate of entrance to the system. So, and then that's where we said that we are going to basically multiply this lambda by 1 minus pi c, because that's the percentage of the time that the system is not full. So in this percentage of the time, those people that arrive to the system that can actually enter. So the rate of entrance to the system is going to be lambda multiplied by 1 minus c multiplied by W. So instead of just using lambda, which was the case in other system, we say lambda multiplied by 1 minus pi c over W. So I just mentioned that to refresh your mind with the whole concept, with the fact that here we need to calculate the rate of entrance to the system. The rate that we have in the problem statement is the rate of arrival to the system, but we need to calculate the rate of entrance to the system. And this green is basically what we calculated as the rate of entrance to the system. Okay, so here you say on average, how many potential customers can enter the system? So obviously, that basically wants the rate of entrance to the system, and that means I have to calculate lambda multiplied by 1 minus pi 3, because see here the capacity of the system is 3, so lambda multiplied by 1 minus pi 3, and to calculate pi 3 equals to rho to the power of 3 pi 0, rho equals to, oops, rho equals to 3 over 2, we just calculated, to the power of 3, and pi 0 is 16 over 130. That gives me pi 3, which is going to be 0.415. And so that means the chance of having 3 customers in the system, or the chance of the system being full, is 40% of the time. And then if I have pi 3, then I can calculate the rate of entrance to the system. So then I will say lambda multiplied by 1 minus pi 3. Lambda is going to be 3 multiplied by 1 minus, that's going to be 1.75 customer per hour.
Professor?
Yeah.
3 divided by 2, right?
Here? Is
For
it,
the lambda?
it's just the lambda, right?
Oh, never mind. You're right. I'm thinking of row.
No, yeah, lambda is 3 customers per hour arrive to the system.
Professor, can I ask you a question?
Go ahead.
Why are we calculating using the littles formula? Why don't we use the long formula that we already have? The rho 1 minus c plus 1 rho to the power of c. We can't use that formula for L?
Here, actually, we don't need L. I just mentioned that to remind you of this discussion that we had in past Monday about the fact that the lambda that we put in all the formulas so far is actually the rate of entrance to the system. And here in the limited capacity system, the rate of entrance and the rate of arrival to the system are not equal. So that's why we multiply lambda by this to calculate the rate of the arrival to the system. But you cannot, that formula that we calculated is actually for, wait 1 second. That formula that we previously calculated is for MM1 system.
Yes, but I mean, last time we had the formula that lambda is equal to rho 1 minus c plus 1 times p times rho to the power of c plus c rho c plus 1.
Let me see.
I think that's like how to use, like the question is asking us, like I just want to make sure like the question is asking us for the customers in the system, so we're calculating L, right?
No, here the question asks, on average, how many potential customers can enter the system? It wants us to calculate the rate of entrance. The question asks for this.
Okay,
The rate of entrance to the system. Not how many people are in the system, how many people can enter the system. So we have the rate of arrival, but not all the people that arrive to the system can enter because the system has limited capacity. So what percentage of these people who arrive to the system can enter? Of these people, so this is the rate of people who enter the system, but what percentage of them can enter? They can enter the system in percentage of the time that the system is not full. This is what it means.
Okay, yeah, I thought we are solving for L. That's why I was like, why didn't we use the other formula?
No, I just mentioned, I said in parentheses, I just mentioned that because I wanted to just remind you guys of the whole concept of arrival rate and entrance rate.
Perfect, thank you.
For the systems where we don't have limited capacity, we don't need to worry about this concept at all. The lambda that we have, the rate of arrival, is the rate of entrance. We don't need to worry about anything. But for this system that has limited capacity, the rate of arrival is not always equal to the rate of the entrance. So,
yeah, I was confused. I thought we were calculating for L. That's why I was
no. Okay, so yes. This is what question wants from us. The rate of entrance. What percentage, on average, how many potential customers can enter the system, let's say, per hour? That's the rate of entrance. And that's how we calculate the rate of entrance. So 3 customers per hour arrive to the system, but about 2 customers per hour can enter the system. This is what it means. Because the system is full about 40% of the times. That's what we calculate for pi 3, right? About 40% of the times the system is full. So really the rate of entrance to the system is about 2 customers per hour, or although about 3 customers per hour arrive to the system. This is what it means. Is there a question? Okay.
And so far.
Good. One more thing, which I'm not sure if I mentioned in previous session, but I may, but if in this system, in the M1 GD C infinity, in this system, if lambda equals to mu, then pi j is going to be 1 over 1 plus c. No matter what is j, j is going to be from 0, 1, all the way to c. So no matter how many people are in the system, which is going to be possibly from 0 people or 1 person or 2 people all the way to c entities or c people in the system, pi j for any one of them is going to be 1 plus c. Again, this is following the condition that, remember, we always want rho to be less than 1 and greater than or equal to 0. So this is the condition we want for all the queuing systems. We don't want even rho to be equal to 1. However, for this type of queuing system, only for this one, we say that it's okay if rho is greater than or equal to 1 as well. It's okay. The example we just solved is the scenario when the rho is greater than 1 and there's no problem. If rho equals to 1, then this will be the formula for pi j. Okay. Just write that in your formula and put a box around it, and make sure to write it in your cheat sheet, because sometimes it may give you examples when lambda and mu are equal. Then in that scenario, you have to make sure to use this formula, which is going to be our next example. Example 2. In this example, we have 2 barbers. Barber 1 charges $11 per haircut. And takes 12 minutes for each haircut. Barber 2 charges $5 for each haircut and takes 6 minutes for each haircut. Okay. Now, we also know that on average, 10 customers per hour arrive to these barbers. It doesn't matter, barber 1 or barber 2, 10 customers per hour arrive to each one of these shops. And the capacity of each one of these shops is 4. They can hold only 4 customers, each one of the shops. And we want to see which one of them earns more money. Okay. So to be able to calculate that, I'm going to find out how many customers per hour can enter the system, and just multiply that by the charge, how much money we are going to charge each one of them per hour. Okay. So basically, to see how much each customer earns, I'm going to find out number of customers that enter each system per hour. So these are the customers that really can enter. Finally, they enter the shop per hour. So these are the customers that can enter the shop. So at the end, they will get their haircut. So I will multiply this by the charge, the dollar per customer, the charge that we are going to have per customer. That can give me a sense of the potential income per hour. So that is going to be the potential income or revenue per hour, and each one of the stores that has higher value in terms of potential revenue per hour, that's the one that we are going to pick. So number of customers that enter the system. So what should I calculate? The number of customers that enter the system per hour for Barber 1.
Question, Professor. Shouldn't we look at is that the same amount the people that exit the system? Because we want them to exit the system, right? Because that's when they pay.
But how do you calculate exit? We always have the possibility of arrivals and everything.
Okay, gotcha. Thank you.
We don't have, if it was simulation, yeah, I could run the simulation for 1 hour and find out how many people have left the system. And that's why I said potential income per hour, because it's assuming that I can just finish all of them in 1 hour. But those are basically, those are the people who have entered the system. So they will definitely receive the haircut and I will gain the money.
Okay, gotcha.
So for Barber 1, if I want to calculate the number of customers that have entered the system per hour, that means the rate of arrival, the rate of entrance, I have to multiply the rate of arrival by 1 minus pi 4, right? Pi 4 is percentage of the time that the system is not full and everyone who is arriving to the system can enter. So lambda, the rate of arrival, multiplied by 1 minus pi 4 gives me the rate of entrance to the system. So for Barber 1, the rate of arrival is what? 10. For both of them, on average, 10 customers per hour arrive. So that's going to be 10 multiplied by 1 minus pi 4. So to calculate pi 4, which is rho to the power of 4 multiplied by pi 0, and then pi 0 is 1 minus rho over 1 minus rho to the power of c plus 1. Rho here is lambda over mu. Lambda is 10. What is the mu here for the first barber? Takes 12 minutes for each customer to do the haircut. What is mu? What is given here? The service rate or service time?
Service time.
So this is service time. How do we calculate service rate?
1 over 12.
So the service rate, which is mu, is 1 over 12 customer per minute. And if I want to find out how many customers per hour, I multiply it by 60 minutes per hour. And that's going to be 5 customer per hour. Okay, so that's mu for the first barber. So now that we are here, actually, let's calculate mu for the second barber as well. So it says takes 6 minutes for the second barber to do the haircut. And this is, again, is service time or service rate?
Service rate.
Rate?
Sorry, time.
Wake up, John. I'm kidding. 1 over 5. Oh, sorry, 1 over 6. Customer per minute. Multiplied by 60 again. Minute per hour. That's going to be 10 customer per hour. So mu2, I'm going to call it mu2 for barber 2 and then mu1 for barber 1. So mu1 is 5 customers per hour. Mu2, obviously, since the haircut is shorter, 6 minutes, mu2 is larger, 10 customers per hour get the service and leaves the system in barber 2. Okay. So now, if I go back here, so I have 1 minus 10 over lambda over mu, which is 5. 1 over 10 over 5, 4 plus 1, c is 4, and that number is going to be 1 over 31. And then pi 4 is going to be rho, which is 10 over 5 to the power of 4, multiplied by pi 0, which is 1 over 31. That's going to be 6 over 31. And then if I put 6 over 31 and put it in the formula on the top, so then lambda multiplied by 1 minus pi 4, 6 over 31, 16, sorry, no. This is 16 over 31, this is 16 over 31. So that's going to be the rate of entrance to barbershop 1. And then if I want to find out the potential revenue per hour, I calculate that number, which is lambda multiplied by 1 minus pi 4 by the charge per customer. And here we charge $11 per customer. And as we just said, that's going to be $53.23 per hour. Okay, that's for barber 1. Now for barber 2, the rate of arrival is 10 customers per hour again. For both barber 1 and barber 2, the rate of arrival is 10 customers per hour. For barber 2, we just calculated mu2, and it's 10 customers here. We just calculated this mu2. The rate of the service was also 10 customers per hour. So then mu2, the rate of service for barber 2 is also 10 customers per hour. So this is that specific scenario when I said lambda equals to mu, and if lambda equals to mu, pi j is going to be 1 over c plus 1, which is 1 over 4 plus 1, that's 1 over 5. So then I still need to calculate the rate of entrance to the system. So the rate of entrance to the system is lambda multiplied by 1 minus pi 4. Lambda is 10. 1 minus pi 4 is 1 minus 1 over 5, because we just calculated that pi j for no matter what is j is 1 over 5. So pi 4 is 1 over 5. So that's going to be 40 multiplied by, divided by 5. And then the potential revenue per hour, I have to multiply this 40 over 5 by $5 per hour that they charge. I'm sorry, for $5 per customer. And that is going to be $40 per hour in this system. So the comparison is between this number and this number. So obviously barber 1, although it takes a lot longer to do the haircut, but since it charges $11 compared to $5, at the end of the day, it has more revenue per hour compared to barber 2.